Hi, and welcome to the SAME webinar, Advances in High-Resolution Site Characterization. My name is Nicole Matthews, and I'll be available to assist with most technical issues that may arise. If you have any trouble connecting, please call WebEx at 1-866-779-3239. You can also send a direct message via the Q&A box. During the presentation, also, please use the Q&A box to submit your questions to our panelists. Finally, this webinar is being recorded. A link to the recording will be made available to all attendees. Thank you for your participation today, and I'll now hand it over to Tim Fitzpatrick.
Thank you, Nicole. Hello, everyone. On behalf of the Society of American Military Engineers, I'd like to welcome you to the webinar entitled Advances in High-Resolution Site Characterization. I'm Tim Fitzpatrick, Business Development Manager for Access Analytical Services, and I'm going to be your host for today's webinar. I also serve as the Vice Chair of Education for the SAME SAME National Environmental Committee, who is sponsoring this webinar today. The mission of the Environmental Committee is to enhance professionalism, create value for the civil service and military members, and provide true training and a forum for interchange of ideas. The Environmental Committee seeks to achieve this mission through several avenues, including guest speakers on relevant topics during monthly conference calls, supporting conferences that promote environmental awareness and committee objectives, and special membership meetings at the annual SAME JETSI conference to recruit new members and promote environmental committees and mission. In an effort to engage industry members of SAME, we have planned this webinar. We hope that the information presented will be useful in evaluating which high-resolution site characterization techniques might be applicable to your individual sites. Following the webinar, the presentation will be emailed to all attendees within 3 business days. Watch for a follow-up email containing the presentation, PDA certificate, and a link to a recording of the webinar. This webinar would not be possible without our presenters, so I'd like to sincerely thank all of them up front for their participation. I'd also like to thank each of you for joining us today. I'm looking forward to the presentation and to your questions afterward. I encourage each of you to send your questions as they arise. As Nicole said earlier, if you type your questions in the WebEx Q&A chat box and click on Submit to all panelists, we will answer as many questions as time allows during the webinar. And now I'd like to introduce our first speaker. Nick Welty is the Director of Site Investigations for Arcadis North America. He specializes in dynamic, adaptive, high-resolution site characterizations with real-time 3D hydrostratigraphic and plume modeling, and has led the first commercial applications of several advanced site characterization tools and strategies. Mr. Welty has presented internal and external workshops to regulators, clients, and consultants on innovative site characterization strategies, and he leads the Arcadis-wide training initiative to improve high-resolution site characterization methods for geologic, permeability, and contaminant mapping. He co-authored the upcoming Remediation Engineering Design Concepts, which explores the history and future of remediation. Without further ado, I'll pass the call over to Nick.
Well, thank you, Tim, for the introduction, and I just want to thank everyone at SAME for having us here today to give this webinar. I'm really excited to be talking about high-resolution site characterization, and I know that Bill, Carl, and John are also. So to give you a little bit of the landscape of what we'll be covering here today, I'll start off and I'll be talking about really the fundamentals and foundation of why do we need to use high-resolution site characterization. So we'll start with the why and talk a little bit about what we need to do instead, which is think about sites in terms of the mass flux that's occurring at them. Bill will build on that. Bill Davis will build on those concepts of mass flux and start to introduce the ideas behind some of the different tools for mapping permeability and aquifer stored mass in low permeability zones. Then Carl Keller will mix it up a little bit, and he's going to talk about some really great methods for profiling in fractured bedrock. So we'll get a bedrock flavor in there as well. And then we'll close with John Soule, who will talk about a few more of the profiling methods for contaminant and permeability mapping at our sites. So my talk is going to focus on, as I said, really those foundations, the reasons why we need to use more advanced site characterization methods. And the title I picked from the talk to really hammer that home is These are the top reasons you should not use monitoring wells for site characterization. So I'm going to start that by showing you an example of some work at a site. This is a site shown with a top-down aerial photo in the upper left, sort of an oblique aerial photo across most of the area, and then a little cross-section in the lower right there. Now, this is a site that, like so many of our sites, was industrial for decades, almost a century, and there were monitoring wells installed to be used as site characterization tools at the site, and that's what you see in that lower right-hand picture. Those monitoring wells were installed in 3 arbitrary zones in the aquifer: a water table interval, interval right above a basal aquitard, and then halfway in between, sort of splitting the difference between those two. Those wells were monitored for over a decade, and based on that monitoring that was completed, the conclusion you would draw about the plume that's present is what's shown on the slide there, that yellow solid. You would come to the conclusion that there is a TCE plume present at the site. It's located really in that shallow zone, and it's low to moderate concentration, several hundred parts per billion. And you would base all your decisions about risk and remedies based on those kinds of concentrations. Well, Arcadis became engaged because the client shared our philosophy on monitoring wells, that they can mislead you and they're not the best tool to understand the true conditions of the site. So we took a look at this site with high-resolution site characterization. And the picture changed from this plume that you see on the slide now to this. So a lot of changes to cover here, 2 main ones. One, we're seeing more colors. Colors represent concentration. So before, we had a maximum concentration of, say, 300 parts per billion. Now we're seeing that orange core. The orange core is 10,000 micrograms per liter. So we're orders of magnitude higher than we were before. And we're seeing it has a larger footprint. So it's higher concentration, it's bigger, and it's present off-site. Well, we went to get our arms around it then, and we did some additional work to refine it, and the picture changed to this. And now we're seeing more structure in the plume, more complexity, and still those high concentrations are present. We then could see that the plume was definitely headed off-site to the right on the page, and we set up transects perpendicular to where we could see the mass flux occurring, where the plume transport was occurring. We could do that based on that initial high-resolution characterization work we'd done. And when we did that, the picture changed from that to this. So now we've moved thousands of feet off-site, and we've managed to map that orange core, which is the 10 ppm PCE contour, at about 80 or 90 feet below the ground surface. And you might notice from this slide that it still has sort of an odd flat shape to the top of it, not very natural looking, right? That's because that was our last transect. So we went out again, and we were sure that we were not going to miss the end of it this time, and we set up transects on the other side of the creek that you see as this sort of ditch up here, and sure enough, we found the edge of this plume. Now, we had stepped out so quickly that there was some structure back in the center of the plume that we sacrificed some of that detail so we could really get our arms around this plume. So we did 2 more rounds of investigation and found that the picture changed a couple more times until this is what it looks like today. So what we were able to achieve was in a fraction of the time that monitoring had occurred at the site, we mapped a plume that extended a mile off-site that was almost 100 feet deep. And the odd structure that you're seeing to the plume is because we didn't just find 1 plume in the area, or 2 plumes in the area, or 3. There's actually 4 separate VOC plumes around this site, and only one of them was associated with our property. There were ones that were actually starting upgrading of it and flowing through it. So some really tremendous benefits of taking the HRSC approach. Now, what I've glossed over some is how did we actually achieve that? How did we change our thinking so that we could map such a large plume in such a rapid amount of time. And that's what I'm going to talk about next. So the way that we are able to achieve these kinds of outcomes is by shifting our mode of thinking about the subsurface away from an older, more conventional approach to site characterization and to thinking about the subsurface to these more advanced methods. So the slide I have up here right now is what we were seeing. So that represents what we were seeing before we started using high-resolution characterization, more of a conventional approach to the subsurface. And it's not that you're missing something on that slide, it's a fuzzy picture. You can start to make out some structure to it, but really it's a fuzzy picture of the subsurface. And that fuzzy picture is what we get with traditional methods like monitoring wells. And that might be an acceptable picture if we're taking a brute force approach for our remedies, pump and treat, or we're just going to dig everything up and excavate it. But there's better ways and more cost-effective ways to clean up the subsurface. And that's by moving away from that picture of the subsurface that's fuzzy to one that really recognizes what's actually there. If we're able to, say, clean off that greasy glass and see into the subsurface, we see that there's these tremendous ranges in permeability and structure that are causing really complex distributions of contaminants. And when we recognize that, that allows us to apply different methods for characterization, and that's what is going to be spoken about in our talks today. Bill and John will both be talking about some of the injection profiling tools, and John has some slides on vertical aquifer profiling. But importantly, the reason that we're doing that is because it allows us to apply remedies that are so much more effective at the subsurface. Chemical oxidation, all these in situ approaches that really target the mass that matters in these systems. So from here, we're going to shift and talk about some of those specific reasons how monitoring wells can lead us astray at our sites. And the first reason that I'll cover deals with the fact that we need to separate out characterization from monitoring at our sites. Recognize that they're two very different objectives that we have in mind. And we need to use tools designed for characterization to characterize and monitoring to monitor, but we shouldn't be using monitoring wells for characterization. And one of the good ways to start that discussion is by thinking about the ideas of precision and accuracy, what kind of data we get with wells and characterization. So precision asks the question, is a result repeatable over and over and over again? Do we get the same result? But accuracy asks, is a result correct? Is it representative? Is it the true value of the system? And if we think about this in terms of monitoring wells, we can put a dartboard up to represent what they give us versus what these high resolution, sometimes we call them smart characterization tools. You can see monitoring wells, if we put them in those arbitrary zones in the aquifer, they can be highly precise tools that have very low accuracy. So a nice cluster of darts, but it's offset from the bullseye where we want them to be. These smart characterization, high-res characterization tools may have lower precision because they're not permanent installations, but they're going to have higher accuracy. So there might be some spread to the data, but it's spread around the bullseye, and that's what we really care about the most. Now let's go back to that example from the beginning. Here's a picture looking from the side that zooms into those wells, and now we're showing the plume based on the high-resolution characterization. And let's look at what those wells are telling us now. So the water table wells had sporadic detections, which in the context of the plume that was mapped makes sense. There's sort of a sporadically present plume that's occurring there. But now look at the deep wells. Some of the deep wells are actually too deep to catch the deep plume. Some of them are intersecting a portion of it. But now look at the intermediate wells. Those intermediate wells are clean, and that looks to be the only depth interval in this entire aquifer where you could install a dozen monitoring wells at a single depth and have them all come up clean. So those intermediate wells are a great example of data and source of data that's highly precise, but isn't giving us accurate information about the plume. Now, another way that wells can lead us astray is by giving us a false sense of security that we really understand the system and the plume transport better than we really do. There's two ways that they do that. One is through an over-reliance on hydraulic gradient and using that to predict what a plume is going to look like and use that understanding then as the basis for our conceptual site model. Now, to think about that, let's reflect on what parameters dictate contaminant transport. And at its most simple, it's permeability and gradient. This is as complicated of an equation as I'm putting in the talk here, but the product of those two really determines where water is going to flow. But if you think about those two parameters, they're equally weighted there. But in reality, and in natural systems, they're not anywhere near equal in terms of their variation. So gradient might vary by several-fold at your site, maybe 2 or 3-fold at a typical site. But permeability could vary from a sand and gravel on the high end to a clay on the low end. Now that could be a billion-fold or more variation in that parameter. So we've got an equation where both variables are equal, but one varies by 2 or 3x and one by a billion-fold. So really we should be thinking about this equation more like this, where permeability really dominates where the water flows, the path it's taking, but gradient is still important because it dictates water in general flows from this area to this area. And Bill Davis is going to show you another great slide to demonstrate this, an image at the beginning of his talk. Now, in terms of a real-world example, here's a great example. This is former Reese Air Force Base. And at this site, there's a 3-mile-long TCE plume. And that plume and the groundwater gradient have been mapped by many, many, many data points. And if you just took the groundwater gradient and used that to predict transport, you'd be off by roughly 40 degrees. So a pretty significant difference, especially when you're talking about plumes that could be thousands of feet or miles long. So I said there were two ways that wells can lead us astray with that false sense of security. Now the other one is through an over-reliance on transverse dispersion to give us really thick, widely spread plumes. And here's a site example to talk about that a little bit more. So this is another military site, this time on the East Coast, where we've got a relief location shown as the yellow box, groundwater flow towards the bottom left. And if you took that location and of a release and that groundwater flow direction and tried to contour up the traditional approach to a plume based on transverse plume spreading, you'd come up with something that might look like this. Now, this looks like a lot of plumes that we see drawn in literature, right? That's got that nice oval shape to it. It's got smooth concentration gradients between one contour interval and the next. But not surprisingly, what I'm going to show you next is totally different given the subject matter of the talk here. This is what the plume actually looked like. So it looked very different from that nice oval shape. It was long, it was skinny, it was much higher concentration. And the takeaway message here is if you had a nice, thick, wide, oval-shaped plume, you wouldn't be worried about missing it by putting in a small number of monitoring wells, which is too frequently what we see happen at sites. But now take this plume, long, skinny, and imagine putting in 3 or 4 or 5 or 6 monitoring wells spread across that area down gradient. You could very easily imagine how those wells could totally miss the plume and it could be going right in between them. Another way that wells can mislead us is through the permeability measurements that they give us. So wells will give us an average permeability value for the system, for the block of aquifer. But really what we care about in terms of the remediation hydrogeology domain is not a bulk average for a big block of aquifer. But what's the max value? What's the minimum value? We need to understand those so we can understand cleanup durations and what are reasonable endpoints in the system. So here's a way to think about that. So if you had an aquifer that's mostly fine sand, maybe it's got a sand and gravel seam moving through it, some long-term average from a pumping test might give you a value like 10 to the minus 4 centimeters per second. But if we put in one of these high-resolution permeability profiles like HPT or CPT that Bill and John will be talking about, we see that there's not a single value to that system. That's a gross oversimplification, that there's really orders of magnitude variation in the permeability. And in fact, that long-term average is giving us a value that's too high in the lower permeability intervals and too low in the high permeability intervals. So we're going to under-predict and over-predict in all the wrong directions. So here's one more reason why wells can lead us astray, and then we're going to talk about mass flux for a little bit. So wells are a really poor tool also when we have NAPL at our site, and we're trying to interpret what does NAPL where is the NAPL really present in the formation. So this is a site where there was 15 feet of LNAPL in a well, lots and lots of LNAPL. How do you begin to interpret that if you don't have anything else? What's truly in the aquifer? Well, what we need to use is, instead of methods like wells, is to move towards something like laser-induced fluorescence, the LIF suite of technologies that respond to PAHs present in the formation and log their fluorescence. And at this site, that was done, and here was the result. So there's the 15 feet of LNAPL in the well, and the LIF log that was done directly next to it didn't have anywhere near 15 feet. It had less than 1 foot of NAPL in the formation that was feeding into that well and creating a thickness that was much, much thicker than is really present in the system. So I think we've hit on a lot of reasons why not to use wells and why we need to move towards high-resolution characterization. And one of the concepts that I want to close with is it's not just about high-resolution characterization. It's about taking a mass flux perspective for our sites. And that's really how we can harness the true value and unlock the power of these high-resolution characterization methods is by thinking about mass flux. So let's look at mass flux, because Bill's going to talk about it in a little more detail and how we can use the tools that we're collecting data from to come up with these mass flux-based conceptual site models. So here's a simple block model of a site. We've got a source, and we've got a plume that is emanating from that source. Now, the traditional approach we're all familiar with is you put a well in, you sample it, and you have some concentration. That's the conventional approach to understanding what the conditions are at your site. It's a mass per volume, milligrams per liter. Pretty simple, right? So now we take that and we're going to turn that into flux. So flux, very simply, is taking that groundwater concentration that we measured and multiplying it by the groundwater flow, so the permeability and the gradient. And that gives us numbers like is shown on the screen. You might have 1 pound per year per square foot. That might be your mass flux measurement. So a mass per area per time. Now that's mass flux. Oftentimes people say mass discharge when they mean mass flux. Mass discharge is mass per time. So if you take that mass flux from before and multiply it by the area it occurs in, so for this example, 100 square feet, you'd come up with a mass discharge of 100 pounds per year. Now, the advantage of this mass flux approach is what we can see now that we've established those ground rules. So let's look at that. We'll build a synthetic aquifer here. It's got a layer of sand, a layer of silt, a layer of clay. Each one of those has its own permeability that's been assigned. Now we're going to add 100 parts per million of some concentration into each one of those zones. And we're going to look at the difference in relative mass flux that occurs in those three zones. And when we do that, we can see that the sand zone is orders of magnitude higher than that silt zone, which is itself orders of magnitude higher than the clay zone. That's a really important observation because that allows us to classify the subsurface into zones of transport and storage at their opposite ends. You know, what are the zones transporting the majority of the mass versus storing all of it? But now we're also thinking about an intermediate category, a slow advection zone. These are the zones that are still moving much, much slower than transport, but they're still moving advectively, which is important from a remedy standpoint, because if it's moving advectively, it's mass that we can access and we can treat. Sometimes these differences in relative flux can be hard to grasp just because they're log scale changes. So another way to think about these are that the transport zones are really, those are your fighter jets. They're screaming along really, really fast. Your slow advection zones are your turtles. I mean, that's really the kind of difference in these zones that we're talking about. And then your storage zones, that's like a statue. That's Michelangelo's David standing there. It's immoving. It's really dominated only by diffusion. So if we take that idea that you have a majority of the mass in the transport zones, we can look at the distribution of flux within a system. So here's what we're going to do. We're going to create a cross plot of what percent of the cross section or the profile on the x-axis versus what percent of the flow occurs, and that's going to be the y-axis. So in a perfectly homogeneous system, we would see a distribution that looks like this. So it's a 1-to-1 line. That means that 50% of the flow occurs in 50% of the cross-section. But I think we all recognize there's no such thing as a perfectly homogeneous system. That simply doesn't exist. Instead, we have real-world systems with all kinds of spatial heterogeneity and anisotropy. And in those systems, instead of that perfect 1-to-1 line, we see a curve that looks like this. That kind of curve, we're seeing that 90% of the flow is in less than 10% of the cross-section. And virtually every site that we've looked at in high resolution where we've mapped out this relationship, we see a similarly shaped curve. And this is a really important takeaway because if 90% of the flow is in less than 10% of the cross-section, that means that we can focus our efforts on 1/10 of what we had been thinking prior to using high-resolution characterization. And that there is the value proposition of high-resolution characterization, that it's probably the best remaining tool that we have available to reduce costs at our sites. And it's all because of this relationship. And that relationship is because we have real-world systems. And those real-world systems are created by aquifer deposition. And that deposition process creates these really complex three-dimensional permeability networks in zones of higher and lower mass flux. This is an image of a synthetic aquifer based on a braided stream, and you can see all the complexity present within that. So I'll wrap it up with some conclusions on my last slide, and I'll say stay tuned for this the next talk. I'll pass it over to Bill Davis to talk about tools to map mass flux. And the conclusions that hopefully you take away from this: first, don't use wells for characterization. They're not a good approach. They're great for monitoring once we've characterized the plume. And then we need to move towards that mass flux basis for a conceptual site model, just a much more powerful way to approach our sites. That's my last slide. I'll open it up for any questions before we transition over to Bill.
Plume? What plume or mass flux mapping tools were used in your initial case study slide?
Yes.
Oh, I'm sorry. I think it was on mute there. Did you get that entire question?
Yes. Yeah. What in the first case study example, what tools were used? Yep. Great question. So we used the full toolbox really there. We used the HBT to profile the aquifer permeability. So Bill and John will both talk about that. We used vertical aquifer profiling to understand the distribution of contaminant mass. We used whole core saturated soil sampling, another method Bill will talk about, to evaluate what mass is in those storage zones versus the transport zones. We used passive flux meters to understand the flux within the system. So yeah, we used it all, it feels like. And I think one of the important takeaways there is there's no perfect tool that you can use everywhere in a site. You need to approach source zones where mass is in the storage intervals differently from where you're looking at your downgradient dissolved phase plume. Great question.
All right, thank you, Nick. I have one more question. What compounds does the lift tool that you mentioned work for?
Yes, the lift tool, the LIF. So that works for several different compounds. So the example that I showed was a gasoline spill. So the PAH compounds and gasoline will fluoresce under the tool, and you can map it that way. But we've also used it for other NAPLs. We've used it for your heaviers, tars, and creosotes. And recently we did the first commercial application of a new tool within the LIF family that can be used to map chlorinated solvent DNAPL. And that works by injecting a little bit of dye right in front of the LIF. So really, if you have NAPL at your site, those are great tools to use, and they really provide you that much more accurate picture of where the NAPL is in the subsurface. It's probably all the time we have for questions. I can pass it over to Bill now.
All right, thanks very much, Nick. All right, and our next speaker up, as you mentioned, is going to be Dr. Bill Davis. And we'll do a quick introduction for Dr. Davis. Dr. Bill Davis received his BS degree in chemistry from Florida State University in 1976, received his MS degree in analytical chemistry in 1985 from Florida State, and his PhD degree in water chemistry from the Environmental Engineering Science Department at the University of Florida, which begs the question, who does he cheer for when the Gators play the Seminoles? Bill?
Okay, well, first
I'm sorry, Bill. It was just a joke, I'm sorry. Let me finish your intro. He has worked in environmental analytical chemistry for over 30 years. Dr. Davis was formerly a research chemist for the U.S. Army Corps of Engineers Ecosystem Processes and Effects Branch Environmental Laboratory Waterways Experiment Station, the WES program. Dr. Davis was a principal participant in the Site Characterization and Analysis Penetrometer System, otherwise known as SCAPS, developing sensors for in-situ detection of petroleum contamination, explosives, and volatile organic compounds in both soil and groundwater. Through the SCAPS program, Dr. Davis participated in the development of the DOE Expedited Site Characterization Program and the development of the ASTM Expedited Site Characterization Standards. During his tenure at WS, Dr. Davis was a founding member of the ITRC, Interstate Technology Regulatory Council. He's continued to work with ITRC as a member of the DNAPL and Site Characterization and Monitoring teams. During development of a triad approach by US EPA, Dr. Davis assisted with the US EPA Corps of Engineers, US Navy, Air Force, and numerous state regulatory agencies with triad training. In addition, he worked as a member of the ITRC Site Characterization and Monitoring team to develop the technical and regulatory guidance for the triad approach document, and most recently on the DNAPL team to develop the Integrated DNAPL Site Characterization and Tool Selection Guidance document. He also helped develop training courses for both documents and was a trainer for the web-based training course for the Triad Approach Guidance. In August of 2008, Dr. Davis formed the Triad Environmental Solutions, Inc. to provide Triad site characterization support to clients throughout the U.S. Since that time, he has worked to grow the company, now providing nationwide services for HRSC. And Bill, I'd like to turn it over to you now.
Okay, Tim, thanks for setting this up and getting all of us corralling the four speakers. And I'd like to first, though, thank Nicole Matthews for teaching me how to do a webinar, and hopefully I will be a good student. But I wish I had continued the interruption, Tim, there when you asked me about Florida State and Florida, because I didn't know you had such a lengthy bio for me. Anyway, I am a Seminole, but that's a whole nother story, and we're running a little behind. I want to thank all the participants for showing up to listen to us, and I'd like to thank Nick for showing a picture so you can see just how old I am. So we'll go to the next slide. So I'm going to do a quick overview here of why we need high resolution. I think Nick did a really excellent job. We need high resolution of a lot of different things, but nowadays, if you're looking at trying to do things like inject oxidants or enhance biodegradation through injection of nutrients or microbes or any of a number of other remedial technologies, you really need high resolution conceptual site model that more than ever will benefit from knowing where you've got stored dissolve phase versus mobile dissolve phase. And I will go through just a couple of tools to hit on what Nick was talking about. I know that John Soule will cover a lot more tools than I will, and Carl will cover a tool that is most incredible and gaining more and more favor, and I'm a big fan of. But we will talk about ways to get at K at your site in high res, and then specifically we'll talk about quantitative measurement of contaminants on site in order to support calculating flux, and then we'll talk about how to put this all together. One thing I want to reiterate, which Nick said a number of times, but I always try to remind myself, I get enamored with site characterization for sure, but it's really in support of making decisions about your site, most often about remedial design, and unfortunately, more often than most of us would like to even talk about in remediation redesign. And by that, I mean when remediation has failed. To go back to what Nick was talking about earlier about gradient versus permeability, this is the slide I think he was alluding to, where the red line on the left there, as you can see, some of those people are actually, and they have made a path circumventing the paved circuitous path, and that would be equivalent to putting in a 10 or 15 or 20-foot screen in an aquifer and getting an average K and using those wells to point you in a general direction of gradient. Whereas we all know the real flow of contaminants tends to take these twisty paths on your site, like the picture on the right. I like to think of it in terms of if the world was homogeneous and isotropic, groundwater modeling would work. But since the world is homogeneous and anisotropic, we all have jobs on these sites. So what we're going to talk about is a couple of tools. I've listed a number of tools, and Nick mentioned a few of them, but you know, there are a lot of ways to get at hydraulic conductivity or hydrostratigraphy in general. One real advantage of the hydraulic profiling tool, which we will discuss here next, over the cone penetrometer, for instance, with pore pressure, is that the hydraulic profiling tool actually, if you do dissipation test with it, as well as the profiling, you are able to get an estimate of K directly out of that data set. And there's a lot of various analytical tools to characterize these sites in high resolution, including things like MEP, which is membrane interface probe, and UVOS, which is just one of the family of laser-induced fluorescence tools Nick was mentioning earlier. But there are also on-site mobile labs that can do discrete soil, groundwater, vapor, whatever, and provide you with real-time, high-resolution data on site to help you make decisions about where to go next, just like you do MIP and UVOS. I always like to have this picture of a toolbox with all the different kinds of tools there to remind us all that, and there are a lot of tools, and you need different tools for different jobs. Nick mentioned this at the end of his talk. There are different approaches depending on what decisions you're trying to make at a site, and there's no coincidence that I have a claw hammer on the left with the red handle and a sledgehammer or a handheld sledge on the right, and there's an adjustable wrench, and there's a Phillips head and a flathead screwdriver. You need a full toolbox. And one thing I would argue that today, the toolbox for high-resolution site characterization is pretty darn full. And I want to further stress that the technologies in general for site characterization are very mature. And so I tend not to use the term innovative about these tools because that tends to put people's mind that they are new and untested. Their limitations, their capabilities are well known. So let's go quickly through the hydraulic profiling tool. If you've never seen it, you advance a probe, usually with a percussion like a geoprobe, and you advance it at a constant rate. You are injecting a flow of water that comes out of the screen. You have a pressure transducer inside that measures how much pressure it takes to keep a constant flow. So just like it says, you are measuring the hydraulic head or pressure it takes to keep a constant flow, and you can get head, as this will illustrate. This is kind of complicated. On the extreme left-hand side, labeled EC is the electrical conductivity you get with so many of the various geoprobe sensing probes like the MIP, and it's also integrated in Dakota's UVOS and HPT, which, so you get this second panel over here called HPT pressure, which is just the pressure it takes to keep the constant flow. This third one here called flow is the flow rate. 200 mLs a minute is the standard pretty much for keeping a constant flow, and that sounds like a lot, but you have to understand that the internal diameter of the flow tube providing that flow of water is a 1/16 ID. So on like a 50-foot hole, you may use 200 mLs of water. So it's not injecting much. Then you get the corrected pressure, and the corrected pressure in that pale blue, the aqua line, is actually corrected for head. And you can see on the final absolute hydraulic pressure over here, what we've done is corrected by doing these dissipation tests. If you look at the far right of this slide, you'll see that you stop it and do dissipation tests. These are the 5 points on this line that project back to the groundwater table and allow us to subtract the hydraulic head for depth of water. Once that's done, along with the dissipation test, you can estimate K, which is really the holy grail or the crux of the apostrophe, as Frank Zappa would say, which is this brown thing in the middle. And it goes, in case you can't see very well, from 0 to 100 feet per day is that scale. So on this one, we have probably 10 feet or even less, much less in these non-permeable zones here. One thing to point out about HPT is, along with the electrical conductivity on the extreme left and the pressure, or K, on the other two panels, It's very, very powerful for determining where water flows, where it doesn't. That can be extremely useful even if you're not interested in making discrete measurements for contaminant and calculating actual flux, for telling you where you might have luck injecting if that's what you plan to do. Moving on to discrete measurement, we've got in this case, EPA Method 8265, direct sampling ion trap mass spectrometry, which is basically, it's called direct sampling ion trap because it doesn't have any GC, so you do no separation. That allows the ability to do samples in 2 to 3 minutes per sample, whether it's soil or groundwater or vapor. Again, I want to stress that it's mature technology. It was developed at Oak Ridge in the 1990s and was accepted as a method into EPA SW 846 in 2003. On the left-hand side, you can see various inlets, direct air inlet for vapor that's high concentration. The workhorse is what's called the water purge inlet, where we can do soil and or groundwater. Thermal absorption interface for absorbent traps for vapor, and also the membrane interface probe can be hooked directly to it for speciation. As previously said, it's the basis of EPA Method 8265. Very low quantitation limits, very rapid, and since it's very rapid, by throwing away the GC, you can do up to 80 samples a day. The downside of throwing away your GC is we only use the isotopic mass, if you are the ionic mass of the various ions to identify and quantify. They're the same mass as used as 8260, but since we do no separation, if the ions are the same, if the mass is the same, we have to report it out as a group. The best way to think of it is DCE is DCE is DCE, not 1, 1 or 1, 2 cis or trans, it's just DCE. One thing you can do with it, and Nick said I would talk about this, and I'll talk in more detail in a few minutes about that, is you can do a lot of samples really quick. And so you can do saturated soil sampling, and we'll talk about something we call PseudoGroundwater in a couple of slides. But suffice it to say, you can do a lot of samples really quickly, and you can interrogate groundwater by doing bulk phase soil and inferring the concentration. One thing you get, in addition to just, if you do that, if you do high res, this is a picture of 30 soil samples taken from 0 to 100 feet at a site in Indiana. What you can see in these bigger blow-ups of the vials is you actually get a look at the soil too. And generally when you're doing that, somebody's logging it. And so you get high resolution logging as well. So now we're going to move on to combining these tools, discrete contaminant measurement in either soil or groundwater, and hydraulic profiling. So in this slide, what we're showing here is this is an HPT K-map, and the dark blue is 1/10 of a foot per day. The yellow is 30 feet per day. Red goes up to 100 or 150 feet per day. And what you can see here is all the way from 1/10 of a foot per day to 30 feet per day, which is 3 orders of magnitude. And if we cut this open, which we will in a minute, you'll see there's even higher levels of hydraulic conductivity. So you can get these real high resolution things going, but something to point out here as well is that this is not silt sand clay site. This is a site in Florida where the entire, I think it's about 50 feet, we'll see in a minute, depth here that's visualized is in fact sand. And it logs as a homogeneous, well-sorted sand. And even in sand, you can get these kinds of variations. And that's something I want to point out about the site that Nick presented first, where he showed that plume that was characterized. That site was homogeneous, logged generally by CPT, by geologists when we did discrete soils there. That was generally logged as homogeneous sand, and what you couldn't pick up either at this site or that site is the low level of silt that is causing these radical changes in hydraulic conductivity and therefore in flux. So this is that same site, and it's a little bit complicated, so let me walk you through it. All these scales are the same kind of colors, but the solid lines are the solid posts in this visualization are the K. And as I pointed out before, the K here goes from 0.1 feet per day to about 50. And then the hanging rectangles you see here that are various colors are the contaminant, in this case, naphthalene and groundwater at 4-foot screen, doing vertical aquifer profiling over this. And so you can see there are some places where the naphthalene gets as high as over 10 parts per million, 10,000 micrograms per kilogram. Then the 3D visualization is the flux, the relative flux, with red being a relative flux of a million, and the blue, the dark blue, being less than 1. So what you can see here is, due to those differences, even though the contaminant's only high in the left-hand side, if you look over at the 3D model of the flux over here on the right-hand side, you can see there's some pretty high fluxes for some not incredibly high concentrations, and that's because the water's moving so fast, as Nick showed. This is a real-life example of one of those, what that hypothetical aquifer Nick showed toward the end of his slides. So now we're going to discuss what flux means, what back diffusion means, and things like that. So what we have here is a picture out of, or a page out of Remediation Hydraulics by Fred Payne, Joe Clinton, and Scott Potter. And I believe I've quoted the 2008. I believe it's now out in the 2nd edition. But anyway, what you have in these red areas are advective zones with high K, and then the pinkish area is fine-grained material with low K. And the cutout here of this plane, this one, you're seeing where you have a high K zone with high concentration in the advective zone. And what it's doing is causing fusion into the fine-grained material. Later in the plume life, after, for instance, when you've done some treatment or you had a small source and it depleted itself, you'll have the advective zone go low in concentration, and the stored dissolved phase in the low K zone is higher in concentration, and by diffusion, it will come back in, and this is when you get into back diffusion. Now it's going to be my turn to do some hypothetical. If I can figure out how to get this thing to advance. Well, first we'll do an actual. So here's an actual pressure trace from an HPT with an actual discrete measurement by bulk phase soil in the upper low K zone of PERC at 1 part per million. And in the advective zone down here, we have 10 parts per million. So now I'm going to tell you about measuring bulk phase soil to infer groundwater. I call it pseudo-groundwater because it's calculated, and there's a couple of assumptions you need to make. So let's take that low permeability zone where we measured 1 part per million, or 1,000 micrograms per kilogram. We make the assumption that the soil weighs 2 grams per mil, and the pore volume occupied by the groundwater is 0.3 pore volume. These are nominal values in the mid-ranges for soils. If you have a specific site and you want to get absolute with this technique, you need to take soils and measure densities and measure pore volumes. But generally, let's go with this assumption. And what that means is for us to measure 1,000 micrograms per kilogram in that saturated soil, the soil has to be 6,600 for that bulk phase to be that concentration. And if we measured the hydraulic conductivity to be 10 to the minus 5 centimeters per second, the flux, the index of flux is 0.066. Similarly, though, without the PseudoGroundwater, we measured 10 micrograms per kilogram, 10,000 micrograms per liter in the groundwater, and the K is 10 to the minus 2 centimeters, our index of flux becomes 100. And so, 100 compared to 0.066 is 1,000 times higher. So what that means is in that advective zone, you know, 99.99% of your mass exists and is moving. Now let's get hypothetical. Let's say we measured that same soil and it turned out to be I made an error. Let's say going down using soil density. It turned out to be 1,520 micrograms per kilogram, which turns out you would calculate it up to be the same concentration in the groundwater that's stuck and not mobile in the fine grain as the groundwater that's in the advective zone. You would calculate the index of flux again, and it would still be 1,000 times higher. But at this point, you've got concentration in the fine grain material that's equal to the concentration in the advective zone. And this is actually a point at which you're tipping into back diffusion, which we'll discuss in a second. And let's make a further assumption. Am I in the? That, well, this is the one where it's 1,520. I think actually I made a mistake here, but, oh no, here we go. It's 1,520 micrograms per kilogram, which comes out 10,000 micrograms per liter pseudo-groundwater. But now let's assume that the concentration in the advective zone is dropped to 5,000 micrograms per liter, and now it's still 500 times more flux going through the advective zone, but the concentration is double in the fine grain, and now you're into back diffusion or washout for sure. So this is one of my concluding slides, in that what you see here now is phases or stages of plume life. The top layer of this slide, which is called the invasion zone, is when you're got high concentration in the advective zone, and then you're diffusing in and creating stored mass. Advective washout is when you're starting to have concentration in the advective zone away from the fine grain material and causing back diffusion to occur. And it continues as it depletes, and the shape of the stored mass, as you can see on the right-hand side here, it continues to diffuse into the fine grain matrix, and eventually will become a blob as you get into what's called the diffusive assimilation. And this is what accounts for a lot of what we have seen over the years in rebound for various kinds of pump and treat injection techniques that address what you can get to at the advective zone. But something to keep in mind too is, depending on where you are on your site relative to the source, meaning and how old the release is and whether or not the source has been removed, you can have some of these, all four at least of the top processes going on at once, depending on where you are on your site and where you are in your remediation. So in summary, I'd like to say I hope I've convinced you that measuring dissolved phase contaminant fine-grained material is useful for determining life stage and helping you decide, life cycle stage, and helping you decide whether or not your proposed remedial design will work or what you need to do to get your current remedial design working again. Understanding the location and mass of dissolved phase, of course, with remedial design, and that the tools are readily available and are cost effective. I believe John Soule is planning to talk about more in detail about how these things can be cost effective. So I'll leave it to John. And I would like to thank Nick Welty for some of those slides, Patrick Curry from Arcadis for the information on the naphthalene site with the mass flux, and Brad Carlson for some of the slides from what's now Cascade, used to be Zebra. So I'm open for questions.
All right, Bill, thank you very much. That was a great presentation. I do have 3 questions here for you. The first one is, can the processes you described tell the difference between immobile dissolved phase and fine-grained materials and actual separate phase NAPL?
Actually, that's a good question. The answer is actually no, yes and no. The no part is until the concentration in the pseudo-groundwater calculation exceeds the solubility limit of the contaminant of concern. For instance, for TCE, it's about 1,180 part per million, right? So if you were to do a pseudo-groundwater constant calculation that said you had 3,000 parts per million TCE, you could be assured that you were beyond dissolved phase, right? And in fact, that's the way a number of states direct you to identify a DNAPL at a site, for instance. But up to the point of solubility in the pseudo-groundwater calculation for that contaminant, all you know is you've got something in that immobile phase, whether it's residual saturation, high-level dissolved, or a combination of the two. You can't differentiate. But from a remedials perspective, it's a moot point, in my opinion.
All right. Second question. What are the limitations for using HPT to create high-resolution hydrostratigraphic?
Well, the first one's pretty obvious. You got to be able to push the tool. So if you can't push the tool there, you're going to have to use a borehole and do what Carl's going to talk about next, which gets essentially the same data, either from, you know, highly unconsolidated, fine-grained materials that are can be hard to push, as well as bedrock, of course. And then the other one is, if you're in something like Nick showed a couple of slides with gravel beds, the pumps on the HPT are not able to flow, keep up the sensor flow rate when you get into really conductive zones, much over 100 or 200 feet per day, I think, is where you just can't keep up the flow. But there again, I think it's a limitation, of course, if you really need to know that number. But once again, what you do know is it's fast. There's a lot of flow. And I think John can probably address that question better since he runs that tool. John, sorry.
Yeah, okay. And thank you, Bill. We have one final question, and this one will actually lead us into our next presentation. The question is, what tool, and we may want to open this up to any other speakers who have some input, what tools are available for VOC contamination in fractured bedrock? Is the only real answer to take a bunch of samples?
Wow, that is a great setup for Carl. The last two are actually good setups for Carl's, but yeah, the best tool out there right now for high-resolution VOCs in bedrock is something Carl's going to talk about, which we assisted him in deploying for the first time and has now been deployed quite a few times, and we've done the analysis, is a thing called the felt-activated carbon flute, flexible liner underground technology. That's Carl, so I'm going to let Carl take it from here.
Excellent. Thank you very much, Bill.
Sure.
Now I'd like to introduce, go ahead.
I'm now going to try to move this thing to Carl. Go ahead.
All right. While you're doing that, I'll introduce our third speaker, Carl Keller. Carl Keller is the principal scientist at the Flexible Liner Underground Technologies, also known as FLUTE. He holds 20 patents on flexible liner methods and received the R&D 100 Award in 1994 and the NGWA 2008 Technology Award for the technology. A physicist by training and with a master's, he has been working mainly in the earth sciences since 1992. Carl is located in Alcalde, New Mexico. And if you're ready, Carl, we'll go ahead and turn it over to you.
Well, thank you, Tim. Let me know if you can't hear me. I'm on a speakerphone. So
I can hear you clearly.
So the problem with all of these underground measurements is, where is the contamination, what are the flow paths, and what's the driving head distribution? And another problem that's common with measurement subsurface is that when you drill the hole, you actually spread the contamination, especially if you recirculate the drilling fluid. And the actual open borehole is a path, especially in fractured rock, for contaminant cross-connection. And so both of these situations can be addressed with what I'll be describing hereafter. So first, don't spread contamination with a measurement method. So while drilling the borehole, recirculating the drilling hole fluids during drilling, like in core drilling, and to my surprise, most core drilling apparently does recirculate the drilling fluids. And so a 150-foot hole takes 3 days, and that's a long time to be spreading the contamination. If you leave the borehole open overnight while you're drilling that same hole, you also have additional contamination migration. If you're doing packer testing or you're doing geophysics or some of these other activities, you're still leaving the hole open for cross-connection. So I'd like you to consider the flute sequence of measurements with a single blank liner. So you can use a drilling method that's rapid, that doesn't spread contamination, for example, air rotary or air-coupled or air-driven air hammers. And you can seal the borehole immediately after drilling a well development. And with that sealing liner, you can actually carry a device into the subsurface for mapping the NAPL and the dissolve phase. You can remove the liner after 2 weeks and photograph the NAPL stains and analyze the activated carbon for vertical distribution of all contaminants. And you can immediately reinstall the liner and map the transmissivity profile of the formation. You can remove the liner while mapping the vertical head distribution in the formation. And all of these things are done with one blank liner. So the rest of this presentation, I'm going to try and explain quickly how all of these things are done. Sealing the borehole, mapping the NAPL, with the FAC system, we call it, which stands for the Fluid Activated Carbon Technique, the transmissivity profiling method, the reverse head profiling method, the water flute multi-level sampling system, or actually systems, and all of this can be done with the borehole open a maximum of 1.5 days. A blank liner installation is done very easily. The liner is shipped to the site on the shipping reel, and the liner is inside out. So you slide the open end of the liner over the top of the casing and clamp it and push the liner down inside, and you add water. And so the excess head inside the liner above the water table in the formation is the driving pressure. And as the liner descends, it's going to push the borehole water into the fractures. And this sequence shows basically the eversion process of installing a blank liner. As you can see, the liner is being fed off the reel. It's pushing the borehole water into the formation. And when you get to the bottom, you actually can then remove the liner by pulling up on this red cord called a tether. And in doing so, you can actually pull the water back into the borehole. And you can do this inversion, it's called, as you remove the liner in a stepwise manner that I'll describe later as a very useful process. And so the nice thing about all of these liner methods is you can actually install them and remove them. So the first question is, how well does a borehole seal? And this is a photograph, a snapshot actually, of a downhole camera inside of a liner. And you can see on the left-hand side of this the vugs, and the liner looks like it's painted on the whole wall. What's really amazing is this step and this breakout below the vugs that you see on the left side. There's actually the liner draped over that, and it looks again like it's more like painted on the whole wall. And so the point is, the liner seals very, very well and far better than most packer systems can seal. So in summary, it seals better than packers. It seals the entire borehole. It's easily removable with minimum risk of entrapment. And that's because it doesn't touch the whole wall until it's supporting the whole wall, and as you're coming out, when it's not supporting the whole wall, it's gone. And the blank liner that I just described is used for several other applications. So both the Napple flute system and the FAC are emplaced as a covering of the blank liner. The Napple flute is a hydrophobic covering which wicks only Napple upon contact. The FAC is an activated carbon felt strip sewn into the Napple cover. And the FAC wicks by diffusion, the dissolved phase, which does not react with the Napple flute. The borehole can actually be pumped as the liner is being installed. This is just a drawing, or not a drawing, it's a photo of the Napple cover on a liner. When you remove the Napple cover with the liner by inversion, as you just saw, you'll see that there are stains like this for TCE, stains like this for coal tar, stains like this for xylene, very, very prominent stains. And the tape measure you see next to these liner systems show you exactly at what depth these contaminants are being located. And these are all Napple. So in summary, the Napple flute provides a Napple FAC, a Napple map upon Napple contact. It is an easy addition to a sealing liner. It leaves the sealing liner available for other use. It's complementary to the FAC. By the way, the spatial resolution of this Napple map is, on the inch scale if you wanted to consider the stains. The FAC wicks the dissolved phase from fractures and from the forest phase. It wicks by diffusion the dissolved phase into the activated carbon. It's recovered by inverting the liner. It provides a continuous replica of contamination in pores and fractures. The entire strip should be analyzed, because if you don't analyze the entire strip, you could very well miss a hot fracture. This was one of the early maps. In fact, Bill actually did these measurements. The right-hand graph is the FACT measurement in a direct push installation in Denmark. The three left-hand graphs are the MIP results. And so the point is, the FACT indeed shows you where the contamination is residing. This is another FACT result in saturated granite. And obviously, in the upper part of the hole above 60 to 30 feet, there's very little contamination. In the lower part of the borehole, there's an amazing amount of contamination. And what's interesting is that the transmissivity profile, which I'll describe in a minute, shows that the highest flow zones are actually high in the hole, very little flow deep in the hole. And yet, in this fractured granite, there is such high contamination near the bottom end of the hole. So the FACT provides a continuous map. The analysis is similar to water samples. The results are concentrations per species per gram of carbon. So you can see TCE, PCE, vinyl chloride, cis, DCE, all of these things are in the carbon. And you can look at the ratios, which is very important. So the entire strip should be analyzed. The spatial resolution, again, is within inches if you want to cut the carbon into that many pieces. And we're actually working on a device for reading the FACT continuously. So I'm going to change now to the transmissivity profiling technique. It's fast and high resolution. Here you see the blank liner coming off the reel, going through the profiling machine and down through the casing into the borehole. As the liner descends, it's again driven by the excess head inside the liner, which we maintain constant. The tension on the liner is also maintained constant, and we measure the velocity of the liner descent. In other words, we measure how fast the liner is displacing the water from the borehole. And so as we start down the hole, water is flowing out of all of the fractures. But as we pass each fracture, we seal it off. Since we've lost some of the flow capacity of the borehole, the liner must slow down. So the velocity before sealing the fracture is higher than the velocity after sealing the fracture. And the difference in the velocity times the cross-section of the borehole is the actual flow rate in the fracture that was just sealed. And so you not only locate the fracture, you actually measure its flow capacity. So as I said, the liner descent rate is controlled by the sealing of each flow path and the associated loss of transmissivity. It's also influenced by the enlargements in the hole, and the other controlling features are kept constant. So as you go through an enlargement in the borehole, though, the liner dilates and you have a bigger piston. So as you might expect, if you have a larger piston and the same flow rate, the velocity is going to drop. And so the velocity of the liner drops as you go through an enlargement, but then it speeds up again as you pass out of the enlargement. We actually use a monotonic fit to the velocity curve to ignore these temporary drops in velocity. And so here in the left-hand curve, you can actually see the yellow line is the real velocity of the liner divided by the driving pressure. The driving pressure in the borehole, that is. And the black curve is a monotonic fit. And so where the yellow curve drops below the black curve is where these enlargements have influenced the velocity. But it's very obvious in the large step changes in the velocity curve. The middle curve is the transmissivity that we calculate for the liner travel every half second. And so in the less than an hour travel through this entire borehole, we measure 6,660 transmissivity values, 0 or whatever you calculate from the velocity changes. If you integrate those transmissivities of every half second, from the bottom to the top of the hole, you end up with the third curve. And in this curve, the initial value at about 30 feet is actually the transmissivity of the entire borehole. The value of this curve at 60 feet is 2, that's centimeters squared per second. That's the value of the transmissivity of the entire borehole beneath 60 feet. And the same thing then as you get down to 100 feet. And finally, what this means is that you can determine from this curve the transmissivity of any interval in the borehole. If you integrated those 6,000 data points from the bottom to the top, over every 12 inches, over every foot, you get this curve. And from this curve, it's quite obvious where the flow zones are located. There's a huge flow zone about 130 feet, for example. So why a T profile? Well, it only takes 1 to 2 hours typically, and this one I just showed you took less than 1 hour. You get half-foot resolution of the flow paths. You provide the flow capacity of every flow feature. There's no leakage past the liner, as there is past straddle packers. There's no entrapment by hole slough. The liner is then used to reseal the borehole when you're finished. So the transmissivity profile maps with extremely high resolution all the flow zones, and this is typically, by the way, in fractured rock. If you haven't noticed that already, I'm talking primarily about fractured rock. Some of these methods are actually of use in sediment. But it provides a continuous T profile for use with the reverse head profile, which I'll talk about next. When the transmissivity profile is being performed, we get near the bottom of the hole, and there's little transmissivity left, so the liner velocity comes to almost 0. We stop when it's 1,000th of a foot per second. At that time, we're at this lower interval is labeled Z1 in the drawing. The transducer that was put in the borehole to measure the pressure history in the borehole as the liner was being, as it was descending. So that transducer then is allowed to equilibrate. And so the unsealed portion of the borehole equilibrates with the formation. That formation, call it F1. That formation pressure or head, call it F1. Then we invert the liner and increment up to Z2, and we stop at that position, and we let the borehole pressure equilibrate again as we're measuring it with the transducer. And now, at that time, since it's in equilibrium, the inflow from the interval that we just uncovered plus the inflow or outflow of the initial interval is equal to 0. It's in equilibrium. Therefore, the inflow equals the outflow. We used the transmissivity profile to select the intervals when we wanted to reverse the liner and stop and let it equilibrate. And these dashed lines show you at each elevation where we stopped. So for the first interval, the total flow was equal to 0. The borehole pressure is equal to formation pressure. We uncovered the next interval. You got a new borehole equilibrium pressure. And now if you write those two equations together and sum them and set them equal to 0, the only unknown is the formation pressure in the newly uncovered interval. If you keep doing that, you get this bottom equation, which means that you can calculate the head in every newly uncovered interval by simply letting the pressure equilibrate beneath the liner when you stop. This is a table of the results. The first column is just the positions where we stopped. The second column is the transmissivity below each of those positions. The third column is the transmissivity of each interval that was uncovered. The next column is the borehole equilibrium pressure, and finally the formation head and the water table for each of those intervals uncovered. This is just a plot of the results. Well, guess where the water is flowing into the borehole and flowing out of the borehole? since the equilibrium pressure for the entire borehole is just the water table in the borehole, above about 70 feet, the flow is into the borehole, and then below that level, the flow is generally out of the borehole. This is just a simple calculation because we know the formation head, we know the equilibration pressure in the open borehole, and we know the transmissivity of every interval. Therefore, we can actually calculate the flow into or out of the borehole, and in fact, we can actually calculate a borehole flow meter synthesis. I'm not going to dwell on this, but you may wonder, how can we measure the equilibrium pressure if it takes forever to reach equilibrium? Well, we have a means of doing that. So in summary, the reverse head profile maps a self-consistent head profile in the formation, identifies aquithards, identifies artesian zones, provides input for flow modeling, and indicates the flow pattern and rate in the open hole. Since we've just removed the liner to get the reverse head profile, by the way, I might reiterate, we already have sealed the borehole, we've mapped all the contamination distribution, we've measured the transmissivity distribution, we've mapped the head distribution in the formation. So the liner is now out of the borehole, and this is a good time to do the geophysics, and those that we would suggest are complementary to what I've just described are the video, the caliper log, and the flow meter. And there's not particular use beyond that. So it's time to select the sampling intervals for a multi-level system because you would really like to know what is the contamination that's available in the fractures. And so it's best to select a multi-level system, but which one? Well, I might suggest one that seals the entire borehole, draws directly from the formation, allows ample purging, draws all the samples through PVDF tubing, is easy to purge and sample, is fully removable, allows easy manual head measurements and recording transducers, et cetera, and is fully tested in the factory and installed by experts. Well, guess what? That's a water flute system. It's a liner system that seals the entire borehole with a liner. It defines the sampling intervals with exterior spacers, and it draws directly from the formation through this pumping system, which I'm not going to describe in great detail for lack of time, but that's available on our website. To pump this system, you simply pressurize the pump tube, it's called, the big fat tube in the middle. It drives the water down, closes the check valve, and flows out to the surface. It's very easy to use. Each of these pumping systems is duplicated for each sampling interval, and you can do 10 in a 5-inch hole, or 15 in a 6-inch hole, 6 in a 4-inch hole. So our experience with the system exists over 16 years. As Bill said, these are not new systems. We've used these in boreholes from 2 to 18 inches to depths over 1,000 feet now. We have hundreds of systems in place from all over the U.S., Canada, Puerto Rico, as far as Denmark and Germany. And our common customers are Boeing, Shell, GE, ExxonMobil, Dow, EPA, NASA, Army Corps, and many other discerning customers. We have a less expensive system that's very simple for shallow water flute circumstances. It's the same continuous liner sealing the entire borehole, the same spacers that define the sampling intervals, but the tubing runs straight up to the surface, and so you need to use peristaltic pumping. I'm not going to describe these for lack of time, but in summary, the water flute systems seal the entire borehole. They're all removable. They allow easy sampling, and then we can use in ragged holes and karsts where the liner is sealed wherever a seal is possible and without loss of sealants to solution channels. They're fully removable, as I said. No heavy equipment is needed for field construction. They're used in artesian conditions quite a lot, and they're used in a wide variety of reliable head measurement. They use a wide variety of reliable head measurement methods, including transducers and water level measurements, vacuum water level measurements, and so forth. So why is this considered a low-cost system? Because some people claim these are expensive systems. Well, we publish our prices on the website, and I don't know of anyone else who does. A blank liner is $18.58, Napple cover $6 a foot, FACT $5 a foot. To measure a sample of the FACT is like $80 per sample. So these prices are very low considering the sample analysis costs. And as I said, our prices are on the website. So they are really relatively expensive, but you don't believe it, just call us and ask us for a quote. Thanks for watching.
All right, Carl. Thank you very much. That was very informative. I do have a few questions here for you. First one is, do you need a new liner for each measurement?
As I said in the beginning, I hope you can see you only have to buy one liner to seal the borehole, measure the Napple distribution, measure the dissolved phase distribution, measure the transmissivity profile, and measure the head profile. That's all with one liner.
Great. Second question, what kind of contaminants does the FACT collect?
It's activated carbon, which is notoriously capable of wicking up practically all the contaminants found in drinking water. So we pick up typically in our installations TCE, PCE, vinyl chloride, the daughter products, and anything else that happens to be there. We're looking right now at the possibility of mapping polyfluorinated compounds.
Excellent. We'll look forward to seeing that results on that. Final question for you. Does this technique that you described only work in bedrock applications, or can it be used in situations where the open borehole is more likely to collapse in, say, a more sediment-based environment?
Some of these methods work in sediments. The first FACT measurements we did were actually in sediments beneath a dry cleaning fluid or dry cleaning facility in Denmark, and they were installed through direct push rods, geoprobe rods. Some of these, obviously, if you're going to do a reverse head profile and the hole's caving in on you, that's not probably a very good application. The liner does support the hole in sediments, but we have only done a few installations through sonic casing and other driven casing systems where the liner is left in place as the casing is withdrawn.
All right, very good. All right, that's all of our questions. Thank you very much for your presentation, Carl. We're going to now move on to our fourth and final speaker, and I'll introduce him now. Our last speaker of the day is John Soule III. John is co-founder of Columbia Technologies, president and CEO. John brings to his roles of president and CEO 35 years of experience directing the development of innovative business solutions using science and technology to advance the state of environmental services. At Columbia, John is responsible for the overall direction of corporate activities, the quality of the company's field services, and business development. John is also co-founder of the award-winning Smart Data Solutions real-time data services platform, and has played an integral role in providing clients with real-time decision-making information. John's a former officer in the U.S. Navy Nuclear Submarine Force and holds a BS in engineering from the United States Naval Academy and an MBA from Chaminade University of Honolulu. John is a member of the Small Environmental Business Action Coalition, the Sustainable Remediation Forum, the Society of American Military Engineers, and the National Groundwater Association. John, you're up next. Thank you very much.
Yeah, many thanks, Tim. I appreciate it. And thanks to the Society and to Nicole Matthews for helping put this thing together. And also I'd like to acknowledge a special thanks to my co-presenters today for their sort of lifetime achievement within the industry and the frontiers that they have pursued and conquered here in the high-resolution business. So we've had a long sort of a long trip here, and I'll try to keep this quick and kind of look at things. But our industry collectively, to me, it's important, and I think each of the speakers have spoken to the concept of how do we monetize the value of this high-resolution business And as an industry within the U.S., we're spending a lot of money on it each day in some component of assessment, characterization, remediation, remediation, and doing things of that sort. And I think what we are consistently seeing is that a large majority of the waste and the errors are created from the fact that we really don't have representative samples of the very heterogeneous environment that's down there. And there's a lot of studies that speak to this, a lot of documentations that look at that. So if you bring it down to the level of your individual sites, or probably appropriate, your portfolio of sites, it doesn't have to be a large plume, a 3-mile plume, a big expensive project in order to understand, the value or the monetization of taking a look at something with a high resolution. You can take something as simple as a small LNAPL site that's got multiple trips for multi-phase extraction, or you're running remediation systems on those for numbers of years. If you start adding up the dollars and cents on that, you're facing a fairly large bill that's accruing with no endpoint in sight. If you're looking at new sites or new problems that are into your portfolio, you say, well, how do I monetize or manage this portfolio of sites as we look down into the future? So what I'm going to do is kind of show a couple of simple examples of, talk a little bit about the tools, but show an example about how to deal with this heterogeneity, how to take this, this mature technology and use it in an everyday application. So I think Nick and Bill both went through a good discussion of the heterogeneity. I really enjoyed, Carl, your presentation on how that then applies into the bedrock scenarios, and it's impressive the progress you've made in that particular arena. So, so I'm now presenting. So we're going to talk about dealing with the heterogeneity with these high-resolution tools, which we have talked about it, and I think Nick and Bill both pointed out that. Another way, I like to look at monitoring wells and use the analogy of it's like taking the temperature of your sick kid. The temperature, a monitoring well is like a thermometer. It'll give you an indication about what's going on at your site, but it's not going to give you really what the problem is and where the source is. And I think we've seen in a couple slides already that we really have to get to the mass that's in the soil and not into the thermometer reading of what the water's telling us. The water's giving us that mass flux and that mass discharge component, but it's really coming out of the soil and where we're finding the majority of the mass. So all of these tools that we've talked about are aimed at trying to focus on where is that mass and how do we tackle it. And so, as Nick did it, and I'll put a little cartoon up there, let's not go out there with our eyes blindfolded and miss the target of what we're really trying to get to. So the beauty of the high-resolution tools box is to be able to apply a number of different tools to get our arms around where the problem is. So the approach is, and we've seen it somewhat described, is let's go after the source zones and understand where the problem's coming from, and let's get that problem isolated and bounded so we know where it is. And oftentimes we go out and we collect a limited set of data, or as Nick pointed out, in the old days we would try to characterize a site with monitoring wells, but we really wouldn't get the resolution that we needed in terms of isolating the source area and the soil structure around that. So once we have that isolated, then we want to try to evaluate these pathways, these little individual highways of contaminant flow, and a strong emphasis there on these transects that Nick pointed out. That does then get us down to targeting some very specific flow paths or mass flux discharge paths. and that's where we're going to go take the high-resolution samples. And so it's sensor technologies, it's flute technologies, it's sampling, and it's analytical technologies, all designed to basically give us a high data rate. And what that high data rate is attacking is the geospatial heterogeneity of the site. And so oftentimes the term high resolution gets thrown around with, you know, I need a high resolution survey, and they're thinking, well, I need one of these tools. And I think it's very important to keep in mind that we're really talking about a toolbox. So we start with the geology. We've got to understand what that is. I think all of us have emphasized that. Oftentimes, work plans tend to start with the chemistry and the water concentrations. And again, those are only really indirect indicators of what's going on. We've got to understand this geology and hydrogeology before we can go forward. Bill introduced us to the hydraulic profiling tool. This tool's been out in active use now for probably just a little under 5 years, I would say. It does differ from a cone penetrometer in that it's actively pushing that water into the formation, so it's actually measuring whether the formation will take water or not. It's very similar to what Carl's doing in the consolidated formations, but we're pushing water into the formation. And so if the pressure is low, we're going to see more permeability. And if the pressure is high, we're going to have less permeability. So we're going to get this very discrete picture about what's going on in the HPT. You do have other methods of measuring permeabilities of the soils. You've got HPT, you've got cone penetrometer as an indirect measurement. You've got the methods of, obviously doing pump tests on formations depending on your screen intervals and sizes. There's pneumatic slug testing of formations that can do some measurements. And each method has a range where it is effective. HPT is not a real low K tool. It doesn't work very well in very, very tight soils. And I think that upper end, Bill, if I'm not mistaken, is about 85 feet per day is where we call it. But as you point out, once you're up in those ranges, you're high. And that can be taken into consideration as you go down your pathway of your remediation design. This is just a quick cross-section out of our Smart Data Solutions, and you can just see, hopefully it shows up. We're displaying both the hydraulic profiling pressure, but then in the aqua colors is the actual derived estimated K. And you can see that it does vary quite a bit across the site, and it's another way of visually showing what Bill showed in the three-dimensional model of the K variation across the site. And that's going to affect, in a great deal, it's going to affect the distribution of the contaminant moving forward, as well as the storage of those contaminants. Understanding the chemistry. Things change in the formation. Things change as a result of remediation. Things change with time. And knowing what the sensors will see and not see. This just is a quick example of, here's the same site, same contaminant, but we've got a disparate distribution. In this case, I'm focusing on a membrane interface probe. We're looking at photoionization detections up here in the shallow zone, and we're still picking up the chlorinated materials in the deeper zones. And what we've got going on is a degradation path that's been created by some remedial efforts. So you'll also get this variation about what's going on, which again adds to the heterogeneity of what's going on the site. Understand the sensor capabilities and or the lack of capabilities. So each detector and each sensor that's used has a range of performance, has certain compounds that it'll perform for, has certain physical properties of compounds that it'll work and won't work, and so understanding that it isn't one tool, one compound when you're down there is very important. So I threw a couple slides in here around membrane interface probe. MIP is just a good general VOC tool. That's the best way to look at it. It comes in a lot of different varieties today. but it'll give us a pretty detailed profile of groups of compounds, and you can drive it to do other things in terms of sampling off of it, as Bill described into the ion trap. You can pull samples, put them into other scenarios. This is just a simple display of membrane interface probe with a halogen-specific detector, which gives us a very large linear range response, 20 measurements per foot of any halogenated compound. So this is going to be your typical PCEs, TCEs, carbon tests, that sort of thing. An alternative detector that's been used in the past is the electron capture detector, or even the dry ELCD detectors. We like the XSD because of its large linear range and the discreteness of the data we get it. So if we push a tool, we pick this kind of response up, we know we're looking at chlorinated compounds. If we add in the photoionization detector and we get a dual detector confirmation here, we can see that we're looking at 3 different zones. I think this works if I go like that. We're looking at 3 different zones of chlorinated response. And so the next question is how do those match up with a hydraulic profiling tool? Well, we've got 2 detectors now confirming that we're looking at chlorinated ethenes in that particular formation. If we then pick up this 3rd detector, so we added a flame ionization detector, which is going to respond to carbon-hydrogen bonds, then now we've got an indication of carbon-hydrogen up above our chlorinated or halogenated compound, plus we're also picking up a little bit, a 3rd confirmation on the distribution here. This is typically indicative of, again, a degradation going on, and typically it's going to be a methane or a non-ethene type of compound that we're picking up in the shallow surface. So you can see we've had degradation, we've got chlorinated material, we've had degradation, we have evidence of that degradation going on. Very discrete in terms of depths when we're looking at that. On the contrary, if we then have a photoionization response and we have no XSD response, then we know we're looking at an ethene without any chlorinated component to it. Again, you bring in the flame ionization detector, and now we're looking at an FID and PID response. So now we're looking at more of a petroleum-based compound. And so you've got 2 detectors confirming that, and you got a little bit of hit there, another one there, and another one down there. So you're getting discrete depth information, compound specific, if you want, or compound groups versus depth. It's important to know at this point in time that magnitude is not going to be indicative of a specific concentration, or is it necessarily going to be a relative comparison of the different intervals. What we do know is that we do have compound. It is at that depth, and it needs to be put into the work plan now as to what we're going to do with that information. So again, that's a quick look at MIP. Accurately locate and identify the samples. I think Bill has alluded to it as well as Nick. One of the fallacies in a lot of work plans is the methods of sampling lose the structure of the systematic approach. ITRC has the incremental sampling method out there as a guideline. The concepts behind that is to be systematic as to how you sample. Don't guess that you think you know better where to sample in the formation because we're going to take one right at the groundwater interface and we're going to take them every 5 feet or whatever it is. You need to be systematic of what that is. 5 feet may be the increment if you want to use it, but it's not where the soil changes color. It's not necessarily with that. If you want to use those additional samples, fine, but make sure you maintain a systematic approach to the sampling methodology. And so a typical soil core, instead of being cut, based on the operator's eye, so to speak, we want to basically use a very systematic approach to that, use something like an on-core sample or something that's going to trap the samples in a fully saturated condition. Then we're going to go in and look at the pathways. So back to the membrane interface probe, now we're going to merge the HPT operation or data sets with the membrane interface probe So there's that same pressure curve we were looking at earlier, same XSD PID response. And so what we see is, to the terminologies that Nick presented earlier, is we've got lower pressure, higher permeability, and higher response. So this is going to be our transport zone in this location here. Most likely, based on the level of response, it's a higher concentration, but we'll need to measure that to be sure. And then we've got probable storage, which will lead to future rebound, as Bill described. We've got response down here, but it's in the tighter zone of the HPT pressure. So there's a very simple picture of transport versus storage with one push with a membrane interface probe, or MIHPT probe. Based on that type of profile, and depending on where you are in the work plan, then go in and do discrete samplings. And there's many different kinds of discrete samplers out there. And when I say discrete, I'm talking about targeting that actual vertical interval of either response off the MIP, or if you're using the incremental, systematic incremental approach, but not the large screens that Nick highlighted have an issue out there. So a simple case example, this is a dry cleaner. You can apply the same concept to small manufacturing facilities. You could apply it to the numerous vapor extraction systems that are running off of some either LNAPL or even chlorinated dry cleaners out there around the country on the many military bases. And so there's large portfolios of these small sites where we've done multiple years of remedial efforts, multiple rounds of injections, extractions. This one happens to be in a saprolitic soils, and we'll just look at it after three rounds of efforts to go take a look at it. This is what the first push out in the parking lot looks like. So it's that same MIP response. And you can see again, we see the ethenes up shallow in it, so evidence of the remediation that's going on, but we still, after a number of years, still have evidence of the chlorinated compounds down at two different intervals down in this location. You move a little bit down gradient, or I'm sorry, the same location, add in this case, the electrical conductivity Bill highlighted, and what we see is we actually have the ionic, evidence of the ionic compounds left over from the permanganate injections that occurred. So you can see the permanganate has moved into this, is residual into this particular zone, but it's not in contact with our PCE primary parent contaminant. So we're not going to finish the degradation or finish the degrading or remediation of the site until we get those two connected. Gets a little bit messy here, but here's the permeability picture again. So you see we have a very high permeability in there, and that's where we see the permanganate is preferentially situated. So it's sought that path in terms of residual work, but we still have chlorinated compounds down in here that are, looks like in a little bit of tighter zone down in that location. Go closer, kind of clean it up a little bit. Again, you can see here's the permanganate response, and then our primary compound is below that. And if we go, so the bottom line to that is, even on a small set of sites, or small sites, and you have a portfolio of these, you can use these tools to drive your, focus your sampling, and then focus your remedial design plans off of that. So let me stop there and see what questions. I know we're just a couple minutes towards the end of the presentation here. So back to you, Tim. Yes? Are we there?
Hey, Tim, this is Nicole Matthews. Is your line possibly muted? We can't hear you.
Hello? Can you hear me?
Yes. Now.
Thank you, Nicole. Yes. Okay. Back to you, John. Yes, we do have a couple of questions for you. First one is, can the process you described tell the difference between immobile? Oh, I'm sorry, wrong question. How can we get more quantitative data from high-resolution characterization and direct sensing?
Okay, good question. It's a common question that comes up. So high-resolution tools in sensors, remember that we're talking about something that's in direct contact with the soil water vapor matrix. So you've got an open pathway. You don't have a measured volume per se. So you're going to get for the most part, a qualitative response. And so you can get a relative qualitative response, and you can drive it to semi-quantitative. But again, to Bill's point, you need this toolbox now. You now need to go in and target your sampling so you can take apart those sensor responses into specific compounds and to specific concentrations. So you're going to need that high-resolution sampling component to go with it, whether it be in the consolidated or unconsolidated soils.
Okay, thank you. I have another question that just came in. On face value, ISM would seem to be in contrast to high resolution. Would not the averaging effects of ISM lead to lower resolution?
Yes. So now there are components of the ISM that go to basically the blending of soil samples and it was designed basically to look at the surface dispersion of samples up at the surface. But the concept of taking discrete samples in a systematic fashion is the part that I would apply to what we're talking about here. So yes, you need to be careful about your process and your protocol, and maybe I should have been more clear when I presented the ISM, but it does speak to the point of being very systematic about the sampling intervals, which again, we're tackling a geospatial problem, and that's important. What we're not doing is then merging those samples into a blended result. So good question. I'm glad you caught that.
Great. Now, one final question for you. The cost for our high resolution seems relatively high. How do we justify the cost to our customers?
Yeah, again, we all get paid to monetize the management of these sites and the resolution of these sites. And so you really have to look at, what's being spent, what are the desired business outcomes for the site, and what's it going to cost to manage that, and how much of the unknowns driving the cost. If you continue to sample the monitoring wells and continue to get the same results, running the same systems, you're just going to basically, burn the candle at both ends until you run out of money. So you do need to look at it from a monetization point of view. But I think each of the speakers have pointed out that the importance of getting the more accurate data up front, not a bunch of precise data that's wrong, so to speak. So I had a friend of mine once said, I'd rather be approximately accurate than precisely wrong. So that's basically the way of looking at it.
All right. Thank you very much for answering those questions. So it looks like that's all the questions we have for today, and we're coming up at the end here. So I would like to take this opportunity to extend a very warm thank you to all of our speakers and to all of our attendees. I'd also like to remind you that after this webinar, you will be automatically routed to a survey page. We'd appreciate your participation in this poll so that we can incorporate your suggestions into future webinars. And therefore, on behalf of the Society of American Military Engineers and the Environmental Committee, we appreciate everybody's participation and hope the webinar has been useful. If you have any additional questions, you can submit them via email to Nicole Matthews at nmathews@same.org. This concludes today's webinar. You may now disconnect. Thank you again and have a wonderful day.